The sound of metal scraping against stone, rubber straining, an engine screaming in first gear going nowhere. Sergeant Tommy Chen wiped sweat from his eyes as his jeep's wheels spun uselessly against the muddy rock face of the Burmese mountainside. Behind him, a convoy of supply trucks waited. Above him, Chinese forces needed ammunition. Between them lay an impossible grade that had already claimed 3 vehicles in 2 days. In 30 minutes, he would either find a way to defy physics or watch good men die for lack of bullets. This is the story of how desperation, a bucket, and the refusal to accept impossible changed warfare forever. But it's really about what happens when human ingenuity collides with insurmountable odds, and what it reveals about the thin line between genius and madness, between breakthrough and breakdown. Burma, October 1944. The Lido Road stretched like a scar across some of the most unforgiving terrain on Earth. 717 miles of mud, rock, and impossibility connecting India to China. Every mile cost lives. Every supply run risked everything. And now, Staff Sergeant Thomas Chen of the 1905th Engineer Aviation Battalion faced a problem that threatened to cut the lifeline entirely. The Chinese 14th Air Service Group needed supplies to keep their airfield operational. The only route climbed grades so steep that even local pack animals couldn't manage them. Standard military doctrine said it couldn't be done. The Jeep's manual specified maximum climbing angles that this slope exceeded by 30 degrees. 3 previous attempts had ended with vehicles tumbling backwards, their drivers lucky to survive. But Chen had grown up in his father's garage in Sacramento, fixing cars with spare parts and stubbornness. He looked at that impossible hill and saw something his training had never taught him to see. He saw a puzzle waiting to be solved. The problem was physics, pure and simple. A Jeep weighed approximately 2,450 pounds, with roughly 60% of that weight distributed over the rear axle. When climbing steep grades, weight transferred backwards, lifting the front wheels and reducing traction precisely when you needed it most. The steeper the climb, the worse the problem became. At angles exceeding 45 degrees, the front wheels would actually leave the ground entirely, turning your 4-wheel drive into an expensive 2-wheel drive that couldn't maintain grip. This wasn't a design flaw. It was the inevitable consequence of the laws of physics, acting upon a vehicle never intended to climb near vertical surfaces. But physics, Chen understood, was just another set of rules. And rules existed to be rewritten. He walked around his Jeep, studying it the way his father had taught him to study every machine. Not as it was designed to work, but as it could be made to work. The afternoon heat pressed down like a living thing, but Chen's mind was racing. Weight distribution, that was the key. He needed to shift the Jeep's center of gravity forward. But how? Sandbags tied to the front bumper would help, but not enough. Moving the spare tire forward might gain him a few degrees. But then he saw it. On the back of every Jeep sat a simple 5-gallon water can, standard equipment for desert operations, but largely unused in Burma's humidity. Chen unstrapped the can and held it in his hands, feeling its weight, imagining its potential. What if the solution wasn't about adding weight to the front, but about strategically removing weight from the back? What if the answer wasn't more complex engineering, but embarrassingly simple physics? That night, while his unit slept, Chen began his experiment. Working by flashlight, he fabricated a simple bracket from scrap metal, positioning the water can directly over the front axle. But he didn't stop there. He relocated the spare tire from its rear mount to the front bumper. He moved the toolkit, the first aid supplies, even the radio equipment forward. Methodically, systematically, he shifted every possible pound from behind the rear axle to in front of the front axle. By dawn, his Jeep looked ridiculous. It resembled a mechanical mule loaded for a pack trip, with gear hanging off every forward surface. His fellow engineers laughed. His commanding officer shook his head. But Chen had done the math. He had shifted the weight distribution from 40-60 front to rear to something closer to 55-45. In theory, that should be enough. In theory. The convoy assembled at 800 hours. 12 vehicles carrying medical supplies, ammunition, and communications equipment for the Chinese airfield. The lead Jeep, Chen's modified machine, looked like a joke compared to the military precision of the trucks behind it. But as they approached the base of the impossible grade, something extraordinary happened. Chen's Jeep didn't hesitate. Where other vehicles had spun their wheels and lost momentum, his climbed steadily, the redistributed weight keeping all four wheels planted firmly on the ground. The angle that had defeated 3 previous attempts became merely steep instead of impossible. His engine temperature rose, his transmission strained, but the laws of physics now worked with him instead of against him. Watching from a reconnaissance position 500 yards away, Lieutenant Colonel James Morrison could hardly believe what he was seeing. Morrison had been in Burma for 8 months, long enough to know that the terrain wrote its own rules about what was possible. He had seen trucks fail, tanks bog down, and men break against the indifferent hostility of the jungle mountains. But here was a Jeep, looking like it had been assembled by a madman, climbing a grade that had been declared impassable by 3 separate engineering surveys. This wasn't just transportation. This was proof of concept. This was a complete rewriting of operational doctrine. The philosophical implications hit Morrison before the tactical ones did. For months, his unit had been told that certain objectives were unreachable, certain positions unsupplied, certain missions impossible. Those declarations had been based on careful calculations performed by competent engineers using proven methodologies, but they had also been based on the assumption that military equipment had to be used exactly as designed, that innovation ended at the factory door. Chen's bucket hack, as Morrison would later call it in his field reports, proved that assumption catastrophically wrong. It proved that the difference between possible and impossible was often nothing more than the willingness to question fundamental assumptions about how things were supposed to work. The psychological impact on Morrison's men was immediate and profound. If a simple weight redistribution could defeat terrain that had been deemed impassable, what other impossible missions were actually just unsolved engineering problems? What other tactical situations could be overcome through creative problem-solving rather than overwhelming force? The entire unit began looking at their equipment differently. Jeeps weren't just transport vehicles, they were platforms for innovation. Radios weren't just communication devices, they were tools waiting to be repurposed. The jungle wasn't just an enemy to be endured, it was an environment full of materials and opportunities. Within a week, Chen's modification had been implemented across Morrison's entire motor pool. The weight redistribution technique, refined through trial and error, became standard operating procedure for hill climbing operations. But the implications went far beyond vehicle modification. Chen had demonstrated something that military doctrine struggled to acknowledge, that expertise didn't always come from formal engineering education or official technical manuals. Sometimes it came from a mechanic's son, who understood that every machine was really just a collection of compromises waiting to be renegotiated. The story might have ended there, filed away as another footnote in the catalogue of wartime innovations, except for what happened 3 weeks later. A similar convoy using Chen's weight redistribution technique encountered enemy forces on a grade that conventional vehicles couldn't climb. The Japanese had positioned machine gun nests specifically to target the bottleneck created by the impossibly steep terrain. They expected Allied vehicles to be trapped at the bottom of the slope, easy targets in a killing field of their own design. They didn't expect jeeps that could climb 60-degree grades with full combat loads. The tactical advantage was overwhelming. American forces outflanked positions that had been considered unflankable. The weight redistribution that had started as a supply problem solution had become a combat force multiplier. Major General William Hoge, commanding engineer for the China-Burma-India Theater, received Morrison's field report on November 15, 1944. The report detailed not just the technical specifications of Chen's modification, but its psychological and tactical implications. Hoge had spent 40 years in the Army Corps of Engineers, long enough to recognize the difference between clever field expedients and genuine innovations. This was the latter. More importantly, it represented a fundamental shift in how the Army thought about the relationship between design specifications and operational requirements. Equipment could be modified, doctrine could be adapted. The definition of possible could be expanded through creative thinking applied to intractable problems. Hoge ordered immediate field testing of Chen's technique across all engineering units in the theater. The results were remarkable, not just for their tactical success, but for their psychological effect on American forces. Units that had been operating under severe supply constraints suddenly found themselves mobile in terrain they had previously considered impassable. Positions that had been written off as untenable became defensible. The simple act of redistributing weight had redistributed the psychological balance of the war itself. American engineering ingenuity, applied to a fundamental problem in physics, had created tactical opportunities that existed nowhere in the official manuals. But the story reveals something deeper about the nature of innovation under pressure. Chen's bucket hack worked not because it was particularly sophisticated, but because it was completely unsophisticated. It required no special materials, no complex manufacturing, no advanced engineering degrees. It required only the willingness to look at a familiar problem from an unfamiliar angle and the courage to test assumptions that had been accepted as unquestionable. In that sense, the modification succeeded precisely because it ignored the proper way to solve the problem in favor of the practical way to solve it. The Chinese forces that received supplies via Chen's modified jeeps never knew about the weight redistribution technique that made their resupply possible. They knew only that American engineering had somehow defeated terrain, that had defeated every previous attempt at sustained operations. To them, the jeeps climbing impossible grades represented proof of American industrial superiority and technical innovation. They had no way of knowing that the breakthrough had come not from Detroit factories or Pentagon laboratories, but from a sergeant with a high school education who had decided that 5-gallon water cans belonged on front bumpers rather than rear cargo areas. This disconnect between perception and reality became a recurring theme in Chen's war experience. His commanding officers praised his technical innovation while simultaneously expressing concern about his disregard for established procedures. His fellow soldiers admired the practical results, while questioning the modification's impact on vehicle warranty and standardization requirements. Everyone agreed that the technique worked, but nobody could quite decide whether Chen was a brilliant engineer or a dangerous renegade who happened to get lucky with an unauthorized equipment modification. The tension came to a head in December 1944, when Chen received orders to report to the Ordnance Technical Intelligence Unit for debriefing about his field modifications. The Army wanted to understand not just how the weight redistribution technique worked, but whether it could be systematically implemented across all motor pools in all theaters of operation. They wanted to turn Chen's desperate field expedient into official doctrine, complete with technical specifications, implementation procedures, and training protocols. They wanted to militarize his innovation. Chen found himself in the surreal position of explaining to West Point-trained engineers how a 5-gallon bucket could defeat physics problems that had stumped formal technical analysis. The officers taking his deposition were polite, but clearly skeptical that such a simple solution could address such a complex problem. They asked detailed questions about stress analysis, metallurgical considerations, and long-term mechanical reliability. Chen answered as best he could, but his knowledge was practical rather than theoretical. He knew the technique worked because he had made it work. He couldn't provide the mathematical proofs that would satisfy institutional requirements for official adoption. The irony was lost on no one except the institutions involved. Chen's modification had proven effective in actual combat conditions against real tactical problems, but it couldn't be formally adopted because it lacked the theoretical framework that institutional approval required. The Army had asked Chen to solve an impossible problem, which he had done. But having solved it through means that didn't conform to institutional methodologies, the Army couldn't officially acknowledge the solution. It existed in a bureaucratic limbo between proven effectiveness and procedural compliance. Meanwhile, in Burma, Morrison's units continued using Chen's weight redistribution technique with remarkable success. Supply runs that had been impossible in October became routine by December. Hill climbing operations that had required full engineering support were being conducted by individual drivers with standard equipment. The modification had become so thoroughly integrated into operational procedures that newer personnel assumed it was standard Army doctrine. They had no way of knowing that they were using a field expedient that existed in official violation of vehicle modification protocols. The psychological effect extended beyond just the immediate tactical advantages. American forces in Burma began developing a reputation for mechanical innovation and creative problem-solving that influenced how both Allied and Japanese forces approached engineering challenges. The Japanese began assuming that American vehicles could operate in terrain that their own equipment couldn't handle, which affected their defensive planning and position selection. Chinese forces requested American engineering support for operations they wouldn't have attempted with their own equipment. Chen's bucket hack had created a psychological force multiplier that extended far beyond its immediate mechanical effects. This brings us to the deeper philosophical question that Chen's innovation raises about the nature of expertise and the source of genuine problem-solving ability. Chen had no formal engineering education, no advanced technical training, no institutional credentials that would have qualified him for research and development assignments. What he had was practical experience with mechanical systems and the mental flexibility to question fundamental assumptions about how those systems had to operate. His innovation came not from superior knowledge, but from the willingness to ignore irrelevant knowledge in favor of relevant experimentation. The contrast with institutional problem-solving methodologies is instructive. When the Army Corps of Engineers analyzed hill-climbing challenges, they approached the problem through established theoretical frameworks that emphasized mechanical limitations and operational constraints. Their analysis was sophisticated, mathematically precise, and completely accurate within the parameters they established. Chen approached the same problem by asking what would happen if those parameters were wrong. His analysis was crude, empirically derived, and effective beyond anything the theoretical framework had predicted. Both approaches had value, but only one produced a workable solution under combat conditions. This suggests something important about the relationship between formal expertise and practical innovation. Institutional knowledge provides the foundation for systematic problem-solving, but it can also create intellectual constraints that prevent recognition of simple solutions to complex problems. Chen's success came partly from his lack of formal training, which left him free to pursue approaches that trained engineers would have dismissed as theoretically unsound. His ignorance of why the modification shouldn't work allowed him to discover that it actually did work. The implications extend far beyond military engineering into any field where institutional expertise confronts practical problems. How many potentially effective solutions are dismissed because they don't conform to established theoretical frameworks? How often does formal training prevent recognition of simple answers to complex questions? Chen's bucket hack suggests that breakthrough innovations often come not from expanding knowledge within existing paradigms, but from questioning whether those paradigms are necessary in the first place. But the story also reveals the institutional challenges that prevent rapid adoption of effective innovations. Even after Chen's technique had proven successful in actual combat operations, it took months for official approval to begin working its way through Army bureaucracy. The modification required evaluation by multiple technical committees, analysis of potential mechanical complications, assessment of training requirements, and development of implementation protocols. Each step was reasonable from an institutional perspective, but collectively they ensured that an immediately effective solution would take years to become officially available to forces that needed it immediately. This points to a fundamental tension between institutional stability and adaptive innovation. Military organizations need standardized procedures to function effectively across large numbers of units operating in diverse conditions. But standardization inevitably becomes a constraint on the flexibility required for rapid response to novel problems. Chen's modification worked precisely because it violated standardization requirements, but its effectiveness couldn't be systematically leveraged because adopting it would require abandoning the standardization that made large-scale military operations possible. Innovation and institutionalization represent competing values that organizations struggle to balance. The story concludes with an ironic twist that illuminates the complicated relationship between individual innovation and institutional memory. By the end of the war, Chen's weight redistribution technique had become standard operating procedure for hill climbing operations in multiple theaters. Thousands of drivers had been trained in its implementation. Technical manuals included detailed specifications for its proper application. But the institutional memory focused on the technique itself, not on the psychological and intellectual process that had created it. The army had successfully systematized Chen's innovation while completely failing to understand what made Chen innovative. This represents a missed opportunity that extends far beyond military applications. Chen's approach to problem-solving, the willingness to question fundamental assumptions, the comfort with empirical experimentation, the focus on practical results over theoretical elegance, could have been studied, understood, and systematically encouraged. Instead, the institution focused on replicating his specific solution while ignoring the general methodology that had produced it. They copied the bucket hack while missing the bucket hacker's intellectual framework that could have generated thousands of similar innovations across every aspect of military operations. In the broader context of human problem-solving, Chen's story illustrates the critical importance of intellectual diversity in addressing complex challenges. His lack of formal engineering training wasn't a disadvantage that he overcame through determination. It was an advantage that allowed him to see solutions that formal training would have obscured. This suggests that effective innovation requires not just technical expertise, but also the presence of perspectives that exist outside established technical frameworks. The most effective problem-solving teams combine formal knowledge with informal approaches, institutional wisdom with individual creativity, theoretical understanding with practical experimentation. Chen returned to Sacramento after the war and reopened his father's garage. He fixed cars, served customers, and rarely discussed his military service. Neighbors knew him as a competent mechanic who charged fair prices and delivered reliable work. They had no way of knowing that his approach to automotive problem-solving had been forged in Burma Mountains, where the difference between innovation and catastrophe was measured in degrees of slope and pounds of ballast. His war experience had taught him that every mechanical problem was really a puzzle with multiple solutions, and that the best solution was usually simpler than the obvious one. The Jeeps Chen modified were eventually retired, replaced by newer vehicles designed with improved weight distribution and enhanced climbing capabilities. But the intellectual legacy of his innovation persisted in ways both obvious and subtle. Engineers who had worked with his modifications carried the memory of their effectiveness into post-war automotive design projects. Soldiers who had driven modified vehicles retained a comfort with field expedience and equipment adaptation that influenced their approach to technical challenges throughout their civilian careers. Chen's bucket hack had demonstrated that innovation could emerge from anywhere, initiated by anyone willing to question whether impossible actually meant impossible. Today, modern off-road vehicles incorporate weight distribution technologies that trace their conceptual lineage directly to Chen's wartime field modification. Electronic traction control systems, active suspension management, and computerized load balancing all represent sophisticated implementations of the fundamental insight that Chen discovered with a 5-gallon bucket and a willingness to experiment. The technology has evolved, but the underlying principle remains constant. Effective hill climbing requires optimal weight distribution, and optimal weight distribution sometimes requires abandoning conventional assumptions about proper equipment placement. But perhaps the most important legacy of Chen's innovation lies not in its technical influence, but in its demonstration of human intellectual potential under pressure. When institutional knowledge proved inadequate for the challenges he faced, Chen didn't accept defeat or wait for official solutions. He approached the problem with curiosity, creativity, and the empirical confidence that practical experimentation could reveal possibilities that theoretical analysis had missed. His bucket hack succeeded because he treated physics as a toolkit rather than a constraint, viewing the laws of nature as parameters to be optimized rather than limitations to be accepted. This mindset, the conviction that creative intelligence applied to intractable problems can discover solutions that exist outside established frameworks, represents Chen's most valuable contribution to human understanding of innovation under pressure. His story demonstrates that breakthrough thinking often requires not more knowledge but the intellectual courage to use knowledge differently. It requires the willingness to question fundamental assumptions, test unconventional approaches, and accept practical results even when they contradict theoretical predictions. It requires, in other words, the intellectual freedom to discover that impossible might just mean temporarily unsolved. The same Jeep that couldn't climb a 45-degree grade with factory weight distribution could easily handle 60-degree slopes when Chen's modifications shifted its center of gravity forward. The vehicle hadn't changed, the terrain hadn't changed, but the application of human intelligence to the interaction between vehicle and terrain had created possibilities that existed nowhere in the original design specifications. Chen had proven that the limits of mechanical possibility are often actually limits of human imagination, and that those limits can be expanded through the simple act of refusing to accept them as permanent. The bucket hack worked because Chen understood something that formal engineering education sometimes obscures. Every machine is really just a collection of compromises between competing design requirements, and those compromises can be renegotiated when operating conditions change. His 5-gallon water bucket didn't violate the laws of physics. It optimized their application to a specific set of circumstances that the original designers hadn't anticipated. His innovation succeeded not by changing what was possible, but by recognizing that what seemed impossible was actually just improperly approached. In that recognition lies a lesson that extends far beyond automotive engineering into every domain where human creativity confronts apparently insurmountable challenges. The difference between impossible and inevitable is usually nothing more than the right approach, applied with sufficient determination to see it through to completion.